Hi, this video lesson is about an introduction into the kinematic formulas, which are the formulas that we're going to use to help us describe one-dimensional motion here in this unit, as well as move forward to help us describe two-dimensional motion and projectiles later on. To get started, I just want to run through this quick list of variables here, as these are the important variables that you're going to need throughout this unit of study as we look at our kinematics. Delta x is our change in position, right? So that's our displacement measured in meters. Again, think x in general, but really that delta x is telling us a horizontal position in some way, shape, or form. If we go vertical, you could change that to delta y to represent a vertical change in position. Again, delta meaning change, that x is telling us a position, right? So that's our displacement. We have our two velocities that we really want to take into consideration, our final and our initial, v sub f and v sub I, respectively there. A would be our acceleration measured in meters per second squared, and delta t would be our change in time. So anytime you approach a kinematic problem, list these variables out. The more you write them down, it's going to help you be able to establish what you know and what you're trying to find. And when you can do that, it's going to better help you pick the formula that you should use to help you solve the problem. Now our first one here, we're looking at our change in position, right? So just like graphically, change of position, delta x is our final minus our initial position. On a position versus time graph, that was simple. You could look at the vertical axis to determine what that change in position was. Here numerically, right, this is what we see. Now, the big thing on this is displacement, right, or a change in position measured in meters, and direction is important, right? So your plus minus, left, right, east, west, north, south, up, down, yada, 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 right? You name it. If one direction is positive, its opposite is then by definition negative. And you need that direction in order to be able to determine your final, your initial. Are we subtracting? Are we technically adding, right? How is this all going to end up coming together here? Our next one is our average velocity. And here we see average velocity as delta x over delta t. Reason why this is an average, even though the definition of velocity is our change in position over time, technically it is an average because if the object is undergoing some sort of acceleration, this will allow us to determine what was the average velocity throughout that acceleration. Or if it's undergoing no acceleration, right, we're moving at a constant velocity, well, then that works out as an average as well, right? So it lets us work it both when we have an acceleration and when we don't have an acceleration, right? It kind of becomes a nice way to look at this. Remember our breakdown for delta, final minus initial. So here we see that broken down as well. So again, just another way of saying our change in displacement with respect to time in meters per second. Same thing, velocity is a vector, so we need to have a direction included. Now, here we see a second way to find our average velocity. And again, this one only works too if we're under a constant acceleration, which for the sake of this physics course, we'll only be dealing with constant accelerations. And again, just kind of rationale behind that is if you take your initial and your final velocity, if you've been undergoing a constant acceleration, you can predict what either your final will be or you can predict what your initial was if you know what that acceleration is. So because it's uniform, you can predict within reason what the initial and the final is going to be because it's going to lie along the same slope if you were to graph this out. So really, we're taking a true definitive average here. We're taking two data points and dividing it by 2 to find an average here. Next one that we're looking at is our average acceleration. Here, again, just like the ones before it, right? Delta v over delta t this time, where velocity was delta x over delta t. So notice how this all stems from displacement, right? Displacement being delta x. Well, if you change your displacement with time, that's velocity. And if you change your velocity with time, you get acceleration. With that, we see our final minus initial velocity over our final minus our initial time. And that's going to give us the unit of meters per second, also known as meters per second squared. So this is how our velocity changes. Your acceleration can cause the object to speed up. It can cause the object to slow down. Acceleration does not always mean speed up. And the term decelerate does not exist within physics, especially within the realm that we're going to talk about it. Use the term acceleration as a blanket. It is a change in velocity, is what it is. And just like the other ones before, we got to have a direction here as well, because that direction is going to help us figure out if we're accelerating and speeding up or accelerating and speeding and slowing down. I was going to say speeding down and slowing down. What this chart is telling us, right, is there's ways that we can determine what an object is doing, either based on a graph or based on a written description, some way, or based on data that you're given, right? You can tell what it was doing. So we have first sign convention. In the left column, we have our velocity, which tells us which way we're going. The middle is our acceleration, which tells us how the motion is changing. And on the right, it tells us what that result is. So what you need to really focus on here is what happens when the acceleration and the velocity are the same and what happens when they're different. If you have a positive velocity, so you're moving in the positive direction, and your acceleration is also positive, they're working together and you're going to speed up. Same thing goes for negative and negative. Your velocity is going negative, the acceleration is going negative, so you're speeding up. They help each other. When you get velocity and acceleration to oppose each other, that means that the direction that it's moving is not the direction that the movement is changing in, which causes it to slow down. I mean, this would be thinking if you're driving and you apply the brakes, you're slowing down. You're still moving forward, but your acceleration is working against you now, so you slow down. The bottom three are pretty, a little more self-explanatory. If you have no acceleration, but you have a velocity, you're moving at a constant speed. If you have no velocity, but you're accelerating, that means your direction is changing. And if you have no velocity and no acceleration, you're staying at rest. So there are your basic kinematic formulas, along with this helpful table to really help you determine how the object is moving, what is it doing, and how is it changing.